So these are my objectives for this talk. In part 1, I'll describe a novel approach to the foundations of quantum mechanics. And in part 2, I'll use this as a basis to briefly apply the model to other major problems in physics, to briefly note the answers to relevant philosophical questions, and to briefly look at how to test the physical implications of the model. In this model, the universe expands relative to the observer. As the universe expands from the perspective of observers in the black galaxy, the red galaxy recedes along a direct line of sight away from them. But as the universe expands relative to observers in the blue and green galaxies, the red galaxy recedes at radically different angles. This creates an obvious problem in the shared universe, an incongruity in the location of the red galaxy. In order to resolve this problem, let's imagine that every observer has their own personal universe. So, for an observer in the black galaxy, the apparent recession of the red galaxy, along a direct line of sight away from them alone, is actually real. But the same thing is true in the blue and green universes. The red galaxy actually does recede at radically different angles, depending on the observer. Of course, we are viewing this whole situation from a God's eye point of view. While every observer in this model has their own personal universe, the model itself is a picture of the shared universe, the community of personal universes. Consider these 5 purple galaxies. As time passes and the universe expands, the red galaxy recedes along a direct line of sight away from each of them. If we could set up a detector in the cosmos and run an experiment from a God's eye point of view, we would see every possible location of the red galaxy hit the detector like a wave. Now let's alter the experiment by placing a barrier with 2 slits in front of the red galaxy. And let's run this experiment from the perspective of the purple galaxy in the middle. As time passes and the universe expands, observers in the purple galaxy see the red galaxy pass through one of the 2 slits, which are close to each other, so the red galaxy could easily pass through either one. If we ran the experiment several times, expanding the universe, rewinding the clock, and expanding it again, the red galaxy would pass through each of the 2 slits at about the same rate, and it would hit the detector like an object, not like a wave. Now let's run the experiment again, only this time let's remove the observer. Let's not let anyone see which slit the red galaxy passes through. This experiment is now unfolding behind the scenes. Without running this experiment from anyone's point of view, this experiment is now unfolding from a God's eye point of view, in a realm of possibility, where the perspectives of all observers who might tune into this experiment are accounted for. As time passes and the universe expands, the possible locations of the red galaxy hit the barrier like a wave, at which point the 2 slits divide the red galaxy into 2 separate waves. The 2 waves then interact with each other to produce an interference pattern on the detector. To summarize, in the terms of this model, the collapsed wave function is a personal universe, while the wave function itself is the shared universe, the community of personal universes. In this way, the double-slit experiment, the classic demonstration of the mystery of quantum mechanics and the wave-particle duality of matter, is explained by this model, by personal universes coexisting in the shared universe. Now let's consider how this model relates to Hubble's law. Edwin Hubble discovered that galaxies recede away from us with a velocity that is proportional to their distance. More distant galaxies move faster than nearby ones. In this model, Hubble's law is reflected in the shared universe. It is explained by the fact that the universe expands relative to every observer in every galaxy. From the perspective of observers in the black galaxy, the blue galaxy receded 1 unit of distance in 1 unit of time, while the red galaxy receded 4 units of distance in 1 unit of time. There is a compounding effect in the recession of galaxies over large distances. But Hubble's law is not reflected at the level of personal universes, which only expand relative to their one observer. The observer in the black galaxy sees every other galaxy recede 1 unit of distance in 1 unit of time. There is no compounding effect in the recession of galaxies over large distances. As previously discussed, this generates a problem in the shared universe, an incongruity in the location of galaxies depending on the observer. To see how this works again, let's combine the two perspectives, personal universes coexisting in the shared universe. Again, observers in these 5 galaxies each have personal universes that expand relative to them alone. For the sake of clarity, let's look at what happened to the red galaxy. After 1 unit of time, the red galaxy exists in 4 different locations, depending on the observer. From the perspective of observers in the black galaxy, the red galaxy began 4 units of distance away. After 1 unit of time, the red galaxy diffracted into 4 possible locations. So, as the universe expands, all observers on this purple line of sight see the red galaxy recede in the same direction. However, from the perspective of any one of them, the red galaxy has diffracted into many possible locations on this waveline. As a rule, once we determine the momentum of the red galaxy, the line on which it recedes, we necessarily become uncertain about its position. To know the momentum of the red galaxy in our personal universe is to be uncertain of its position in the shared universe. On the other hand, once we determine the position of the red galaxy, we necessarily become uncertain about its momentum. The red galaxy could be receding along any line of sight in any direction, depending on the observer. To know the position of the red galaxy in our personal universe is to be uncertain of its momentum in the shared universe. Notice how the uncertainty principle, the foundational tenet of quantum mechanics, which is itself unexplained by quantum mechanics, emerges in this model out of 2 basic propositions, that the universe expands relative to the observer, and there are multiple observers. This is the essential point. Since quantum mechanics itself emerges out of this model, we can use this model to ask questions about the cosmos at the largest scale, with quantum mechanics fully conserved. How do these universes interact with each other? What could those interactions tell us about the nature of gravity, dark energy, dark matter, etc.? We can use this model to ask these cosmological questions in a way that is entirely quantum mechanical. It's worth noting that this is, in a literal sense, a model of quantum gravity, since space-time itself is quantized relative to the observer. So, we've established a conceptual framework for the foundations of quantum mechanics. Now we'll use this as the basis to briefly apply the model to other major problems in physics. Keep in mind that much of this is cursory on purpose. I want to give you a sense of the broad explanatory power of the model, as a way to justify going deeper on any single point. Now let's talk about the observer. First of all, you and I have different observable universes. If we live 1,000 miles apart in a static universe, then I can see 1,000 more miles of universe in this direction than you can. Our cosmic horizons are different. But according to classical models of the universe, this difference is irrelevant. In classical physics, reality itself is defined as an area. Within this area, it is still a fact that you and I have different cosmic horizons, but this fact is unimportant. It doesn't matter to the physics of the universe that you and I see different sections of this area. But we don't actually live in a universe ruled by classical physics. Our universe is also quantum mechanical. Recall what we just learned about the foundations of quantum mechanics. In the simplest terms, an observer is a reference frame for the universe. In this model, every observer is a reference frame for space-time itself. As a result, the fact that you and I have different observable universes is suddenly a meaningful fact. Now, when it comes to defining what constitutes an observer and what does not, consider this. No matter how you define one, every observer will have a unique cosmic horizon. Simply by way of existing at different points in space-time, all possible observers, using any definition of the term, will have different cosmic horizons. Given this fundamental fact about observers, for all intents and purposes, we can treat galaxies themselves as observers. The only assumption we need to make is that observers, however they happen to be constituted, do not arise in the barren voids of intergalactic space, but do arise in galaxies. The idea that observers play a fundamental role in physics has been around for a century. Consider John Wheeler's concept of the universe as a self-excited circuit. The universe gives rise to observers, who in turn give tangible existence to the universe, as the two ends of this circuit exist in a reciprocal relationship. But this approach can be pushed much further than it has been. If the observer's role is truly fundamental, then, again, observable universes are meaningful units of physics. This is an important point, which might be hard to fully appreciate at first. It is as if observable universes were an entirely new type of object. Imagine discovering a whole new category of particles. Like the strings in string theory, observable universes are a newly uncovered abstraction that we can use to conduct new physics. If a playing field of observable universes are interacting with each other, then what are the rules of this game, and what are their consequences? For the sake of clarity, in these diagrams, observable universes will grow at the speed of light in this otherwise static cosmos. As in reality, all observers with the same horizon distance are simultaneous to each other relative to the Big Bang. Let's set the horizon distance of this universe to 5 billion light-years. Now let's run the clock forward 1 billion years. The horizons of the blue and green galaxies now overlap 2 billion light-years at their apex. In fact, every observer that is 5 billion light-years away from the black galaxy now has a horizon distance that extends 1 billion light-years beyond the black galaxy. If they were all accounted for, their overlapping horizons would form a complete circle around the black galaxy, with a diameter of 2 billion light-years. This shaded circle represents a new force of negative pressure in this universe. When two personal universes overlap and expand in opposite directions, they push against each other in the shared universe, which creates a region of negative pressure in between them. Negative pressure pulls together, like a stretched-out spring that snaps back in. However, when different regions of negative pressure interact, their inward pulling energies compete with each other, which pulls the space between them in opposite directions and generates a repulsive effect. And since different personal universes are overlapping everywhere, a repulsive force is evenly spread across the entire cosmos. In this way, dark energy is a natural outcome of different personal universes coexisting in the shared universe. At the same time, as we just saw, in a universe that expands relative to the observer, pressure is exerted back upon the observer's galaxy from every direction, which generates an extra gravitational effect that holds the galaxy together. Let's take a closer look at this effect. In this image of the bullet cluster, which is actually two clusters that have recently passed through each other, the galaxies are highlighted in blue and gas is highlighted in pink. When two clusters pass through each other, the galaxies in each of them are unlikely to collide. But in a typical cluster, the bulk of the matter is actually found between the galaxies in the form of diffuse gas, and this gas is bound to collide when two clusters pass through each other. That's what happened here, and as a result, the gas in each respective cluster was displaced. It now floats in between the two clusters themselves. And this should be the place where gravity is the strongest, since the bulk of the matter is found in the gas. But that is not what we observe. The force of gravity is not displaced along with the gas. Instead, it remains centered on the galaxies themselves. In the context of this model, since the universe is not expanding relative to the cloud of gas, since no observers are there, this region is not a locus for the competing forces I just mentioned. But this is happening around the galaxies, where most of the gravity therefore remains. In this way, so-called dark matter is a natural outcome of two basic propositions: that the universe expands relative to the observer, and there are multiple observers. Consider another outcome of these basic propositions. As personal universes overlap with each other in the shared universe, they push against each other and through each other. The purple shaded section represents the amount of negative pressure generated by this interaction, pushing against each other, while the red shaded section represents the amount of positive pressure generated by this interaction, pushing through each other. These two opposing forces cancel each other out, and what remains is a leftover amount of positive pressure. These two personal universes are pushing through each other slightly more than they are against each other. This happens all over the cosmos, with interactions between different personal universes yielding different amounts of positive or negative pressure. At any given time, the sum total of these interactions cancels itself out, almost, but not quite, completely. So a huge amount of vacuum energy, 10 to the 112 ergs per centimeter cubed, is reduced to a tiny, non-zero amount of leftover energy, 10 to the minus 8 ergs per centimeter cubed, which accounts for the gradual expansion of our universe. The physics community is, at present, fundamentally unable to explain this vast discrepancy between the energy and the behavior of the vacuum of space. But in the context of this model, the vacuum catastrophe is straightforwardly resolved by a universe that expands relative to the observer. Let's talk about testing the physical implications of this model through a phenomenon called dark flow. Recall this diagram, which depicts the expansion behavior of a personal universe, where there is no compounding effect in the recession of galaxies over large distances. It turns out that this phenomenon has already been discovered. In 2008, a group of astronomers observed a large collection of galaxy clusters drifting at a constant rate toward the edge of our observable universe. The flow extended to the end of their measurements, out to 2.5 billion light-years. Their working assumption was that it likely extends across the visible universe. This flow is anomalous in the context of our standard models of the universe, which assume that at the largest scale, galaxies have no substantial momentums. They only have positions in a space that is expanding uniformly. But recall how, in the present model, the uncertainty principle functions at a cosmic scale. According to this model, astronomers have simply been measuring the positions of galaxies at a hidden cost of measuring their momentums. The dark flow experiment was the first inadvertent look at the other side of this coin, measuring the momentums of galaxies at a cost of measuring their positions. From what I know about the setup of the dark flow experiment, astronomers looked at an enormous imaginary sphere of space, and within that sphere, they subtracted the expanding effect of Hubble's law. Then they averaged out the remaining motion to find this unexpected flow. Recapitulating this experiment could be a simple way to test this model and produce more evidence that the universe expands relative to the observer. The aim of fundamental physics is to explain as much as possible from the fewest and simplest propositions. The ultimate measure of success is whether a single model can unify and thereby resolve the various problems of the field. In this talk, I showed how the present model gives rise to quantum mechanics, quantizes space-time, naturally accounts for the other major problems of modern physics, including some not mentioned here, and it makes testable predictions, also including some not given here. Because of that, this model offers lots of different points of entry for collaboration, depending on your interests. We all bring different skills to bear, and that's ultimately what's needed to refine, extend, and articulate this model. I know it's a strange trip that I've invited you on, but hopefully I persuaded some of you that it's worth taking, that this approach is on the right track, that along the way will be opportunities to contribute, to push into uncharted territory, and make new discoveries.